right, y'all. So now our final topic in Unit 3 is called the Scope of Inference. And inference, we can attribute conclusions based on data to the distribution from which the data was collected. So basically, based on data I have about my sample, I can inference something about the population or inference some type of relationship. Now, if a result is called statistically significant, this is an observed change that is so large it is unlikely to have occurred by chance alone. Meaning it's so rare of a result, it's not likely to happen, and since it's very unlikely to happen, we're not going to leave that due to chance. There's some significance to this result here. So those are some buzzwords that you'll see quite often throughout this course. Now, in statistics, random is equivalent to this idea of low bias. If you've randomly sampled, hopefully you're getting closer to the truth, and you're not introducing personal bias or some of the other biases that we've talked about in the course in the earlier lessons here. Now, if a result is statistically significant and randomization is used properly, we can infer a few things. Now, if I use a random sample, as we said way back in the first lesson here, we can generalize to our population of interest or to that target population from which we pulled that random sample. And the reason we can do this is because random sampling helps us to reduce the bias, right? Low bias is random. Now, if we have a well-designed experiment and there's some element of random assignment, now we can infer cause and effect because the differences are due to the treatments and not other factors. And because of this random assignment, it's going to reduce the effects of confounding variables by balancing them out into the different treatment groups that we've formed. Now, it is important to note when using experiments, these use volunteers. Therefore, the results of some designs may only be generalized to people or objects who are similar to those used in that experiment. So you can have random assignment and not explicitly have random sampling, but regardless of what your results are, it would only be appropriate to generalize those results to those similar in the study or objects similar in the study. So those are basically our two caveats, random sampling and random assignment. And ideally you want both so that you can generalize those results to a population and you can infer cause and effect. And here are other reductions from that. So let's go ahead here, take a quick peek at this example question. Typically this does show up at least once or twice in the multiple choice, but it's very common in the FRQ section. So I'm going to give you a few moments here, go ahead and read over this question and try to find the answer. Okay, so hopefully that wasn't too troublesome, but you can see keywords there, random assignment, statistically significant, might be some indication of control groups, different dosages, the treatments, etc. So they can ask you a multitude of questions. But for here, which of the scientist's conclusion is not appropriate? Well, the correct answer is that the experiment only included green beans, so we cannot generalize these results to all of the vegetables, right? So because I only used a random sample or because I only used green beans in my experiment, it would not make sense to say this about tomatoes or sweet potatoes, etc. Things like that. So you're really looking for those keywords, random assignment, random sample. And I'm actually going to reference here some of the FRQs over the past few years, just to get a better idea of what we're looking for. So this one was from our last AP exam here in May 2021. You can see this is an observational study, and so the follow-up questions are, what is the benefit, right? What can you inference from a random sample? But then also, I really like that they also included, if you obtained a statistically significant result, can you infer cause and effect? Well, no, we cannot because this was a random sample, so I can only generalize, I can't infer cause and effect. If we go here to 2019, we see an experiment. Now, it didn't ask us what would happen if we got a statistically significant result, but if we did obtain one, we could say that the mixture of the concentration of the fungus mixture would cause a reduction in the number of insects. Here in 2018, we see another experiment looking at ACL surgeries, and you can see part A there, based on the design, would a statistically significant result allow you to conclude, what would it allow you to conclude? So we're just really looking for that idea here of random sample versus random assignment. Ideally, you want both, but again, experiments typically use volunteers, so it's just usually going to be one or the other. Not always, but most times. Okay, so the scope of inference. And you can memorize this two-way table if you want to, but you don't have to. If you have a random sample and a randomized experiment, you can determine causal relationships and you can generalize to the population. Now, if you have a random sample but an observational study, you cannot conclude causal relationships, but you can generalize to a population. And you'll see there in the bottom rows, the same thing happens. If you do not have random sampling, you cannot generalize to a population. You can only generalize to those that are similar to those that are in your study. And then same thing here. If you have a randomized experiment, no random sampling, you do causal relationships. And if you don't have random sampling and you don't have a randomized experiment, you can't do anything. And that's pretty much worst case scenario. So take a screenshot of this if you want. It'll be in our notes. But let's take one last look at some example problems here, just to get an idea. So many students insist that they study better when listening to music. A teacher doubts this claim as it suspects that listening to music actually hurts academic performance. Here are 4 possible study designs to address this question at your school. In each case, the response variable will be the student's GPA at the end of the semester. What inferences can we make for each study? For each design, suppose the mean GPA for students who listen to music was significantly lower than the mean GPA of students who did not listen to music. All right, so go ahead and pause the video, take a look at some of these designs here, and we'll see what we can infer. Cause and effect, or generalization, or neither. So go ahead and pause the video, and good luck. Okay, so hopefully not too complicated. Now, let's suppose we get all our students in the class, and then we ask them whether or not they listen to music, and then we divide them into 2 groups. No random assignment, no random sampling. There's not really much inference we can have here. Even if there is a statistically significant result, we only looked at our class. Now, let's suppose we select a random sample of students in our school to participate in the study, then we divide them into 2 groups proposed in design 1. Well, now I can generalize to my school as my population of interest, but I still don't have any random assignment, so I cannot infer cause and effect. Here in design 3, get all of the students in your AP Stats class to participate in a study. We randomly assign half of those students to listen to music while studying for the entire semester, and the other half will abstain from listening to music. So now I can infer cause and effect to those different treatment groups if there is a statistically significant difference. But now, because I'm using a convenience sample of my AP class, I can only generalize to my AP Stats class and not to our entire school. Now, we select a random sample of students at our school to participate in the study. We randomly assign them, yada, yada. Well, random sampling, we can infer. We can generalize the results to the population of interest, which is now our school and not just our class. And the random assignment allows us to infer cause and effect to the what they were listening to while they were studying, because that was a statistically significant result. Now, assuming we use both types of randomization methods properly, can we inference these results? Can we say that music actually improves GPA for all high schools in the United States? No, we only took a random sample of our school, so I could only generalize those results to our school. And it was only a 1 sample from our school, so that's not really reliable data. Maybe we just got lucky that it happened once. So you'd want multiple samples from different schools all over to really see, like, what can we say about the relationship between music and GPA? So that's going to wrap up our collecting data unit. So we've talked about a multitude of things in this unit. So I'm just going to do a quick click through here. So it started off in lesson 1, where we talked about types of data collection and the difference between population samples, parameter statistics. We talked about observational studies versus experiments. Then in this next lesson, we talked about types of sampling methods, the different random methods that can be used. Then we also talked about confounding variables, what happens when we confuse our results with some unknown hidden variable. We did talk about bias, and that can be introduced through sampling errors or through undercoverage bias, non-response bias, or response bias. And of course, bias exists outside of those 3 elements as well. Then we started talking experiments, specifically completely randomized designs, the placebo effect, single and double blind studies. We also talked about the matched pairs design and randomized block designs. And then lastly, the scope of inference. So you have everything you need to be successful for collecting data for your AP statistics exam. So stay tuned for next unit, which will feature probability.